It's electric.
In this little worksheet, we're going to try to look at the space surrounding an electric field to visualize it. Before we do that, how about let's review the idea of electric field by writing down the equations for an electric field. E is for electric field. That little half arrow means that it's a vector. What's a vector? A vector is anything that has size and direction. So a real simple example, your GPS in your car. GPS is one of the greatest gifts to mankind. Probably saves a lot of marriages. You know what I'm talking about? Every time we get lost, my children have learned that Daddy's taking a long cut. And I'm just like, shut up. You know, like pull over for directions. No, I know where. Okay? So anyway, your GPS tells you not only which way to turn, direction, but also size. So in 2 miles, turn right and head east. That's a vector, a displacement vector, 2 miles east. Versus distance is what we call a scalar. It only has a size. So in other words, it's not good enough if you're trying to get directions to go to someone's home. Go 2 miles. Like, okay, that's not helpful. But 2 miles east, 2 miles west, etc. So the electric field E is equal to the force F. It's also a vector divided by Q. It's force per unit charge. That's all. So in other words, anytime we have a source of charge, like our little plasma ball here, the space around it changes. Woo! And that's why these things are so fun, because they're filled with a plasma gas that ionizes when it's electrified, so you can actually see that field. So again, I kind of like the idea, the analogy of wind. You can't see wind, but you see its effects. That's what an electric field is. It's like an electric wind. It's a force field that acts on other charges surrounding the space around a charge. Speaking of which, if you think about force, let's review here. According to Coulomb's law, electrostatic force F is equal to K Q1 Q2 over the distance squared. This is helpful for us to write out the equations because now, instead of doing all this crazy math, physics is really not about the math, even though we use a lot of it. It's about the ideas. So for us, we're not trying to make this a killer math class. You're not a bunch of nerdy electrical computer engineers, though maybe one day you will be. That's cool. So somebody who's nerdy enough, they'll do these calculations to make sure that there's enough electrical force to make the electric ink stick to your screen for your next electronic textbook e-reader or the touch screen on your iPhone 19 or whatever. But the idea for us is the amount of electrical force F is proportional to the amount of charge present, Q1, Q2, on each object, and then divided by the distance squared. So the big idea is not only do you need to have more charge present to have more force, but the other factor is what? The distance, right? And the weird thing is it's an inverse square law. So if you move one charge closer to another charge, then the force goes up exponentially. And the way you can think about it is if you move it one charge A twice as close to charge B, well then charge B is also twice as close. Therefore, it's 4 times the force overall, an inverse square relationship. So how's this going to help us? How about this? If I substitute in F into my electric field equation, another way to look at this is if I put in F is K Q1 Q2 over the distance squared, one of the Q's drops out. So what does this tell us? All this tells us is the electric field just depends on how much charge you have present at your source, and then it's inversely proportional to the distance squared. The electrical constant we don't really control there. So here's what we're going to do on this worksheet. There's a bunch of directions, blah, blah, blah. You can read. Okay, I don't want to insult your intelligence, but let me just kind of talk you guys through what's going on. So here we have a positive source. At point A, we want to probe the field. What kind of test charge do you use to check an electric field? You use a, guys remember? What kind of hockey puck? Positive test charge. So even though it's an electron that moves around the outside of an atom, by definition, mathematically, we usually like to have a positive reference frame. We define an electric field by a positive test charge. So if this is a positive charge at point A, I'm going to put a little plus here. What will a positive source do to a positive test charge? It'll push it which way? Away. It's a repulsive field. So what's silly is we're just going to sketch it in at points B through F. But here's what I want you to do to show you that it's not so silly. Go ahead and take your ruler and measure it right on the page there. And I'm going to measure it on my paper just because, on the computer screen, it might be a little bit distorted because I zoom. So it looks like these are all, I don't know what you guys are getting, about 1 centimeter in length. You guys getting roughly that, depending on how it Xerox? So what I want you to do is, if points B through C are all equidistant from the point source there, and it has the same amount of charge, then these arrows, these force arrows, F, should all have different sizes or the same size. Which one? Same size. So at points B through F, go ahead and draw an arrow 1 centimeter in length pointing towards the charge or away from the charge. Which one? away from the charge. That's correct. And the reason why they're all the same length is because they're the same distance away. Mathematically, we could calculate this electric field strength by using the E equals kq over the distance squared. And all it is we would have to know the size of the charge in coulombs and the distance in meters there. But really, the focus of this is not to do all the math, but to visualize what's going on. So a cool way to see this is, again, this electric field hockey simulation here, where we have a positive test charge, we have a positive source, and we know that we're going to have a repulsive field pushing away. See how it's pushing up there? Or another nice way to look at this is this little simulation that we use for electrostatic fields. So this is a repulsive field where the charges are getting pushed away there. If we turn off the flat view and make it 3D, you can think of it like an electric hill where the charges flow down that hill there. We're going to look at this idea called potential. And these are equal potential lines, these concentric rings that go away from the charge, where it's kind of like you store up energy by moving charges up a hill. And really, that's what a battery does. It creates an electric field where you can move charges and store energy against that field. So all of modern life is made possible because we can move a charge from one point to another, which is kind of cool. Anyhow, next question. If we draw a vector at point G, which is way up here, point G is twice as far from the source as the other charges. So you tell me, is the field stronger or weaker at point G? What do you think?